Hello, everyone. Good morning, good afternoon, and good evening based on wherever you are. It's great to meet you all virtually this year over this session, and I hope wherever you are all doing safe. I'm Avik Bhattacharya from Keysight Product Management Team for the Network Test Solution, and I'm working in the networking industry for more than 13 years now. I've seen many disruptive changes in the packet networking domain, and time sensitive networking, or TSN, is of course one of them, which is becoming useful to more than one industry outside automotive, of course. As part of Keysight, I have worked with many companies from different industries that are adopting TSN. In today's session, I'm going to share some of my experiences on their different approaches to looking at TSN as a technology. Let's start by looking at these industries and ask ourselves what is really common between them. Three of these industries from the left: automotive, professional audio video, broadcasting, industrial manufacturing, they were already using some proprietary communication channels 10 years back. And the proliferation of high bandwidth applications made them think about an alternative communication channel that can carry the required data that is necessary for their operation. For example, a surveillance camera video feed or a modern infotainment requires much higher bandwidth and networking flexibility than that the proprietary systems could provide. So they looked for a new communication layer that can scale, and Ethernet was the obvious time-tested choice because of its widespread acceptability in the IT domain. But it was quickly realized that these industries also need applications that are time critical in nature. As a result, the communication data between these applications also need to be time bound. Ethernet historically was not designed for providing low and deterministic latency and also guaranteed delivery. In fact, Ethernet worked on the principle of best effort delivery of traffic. The telecom industry and its 5G network infrastructure part also needed to carry time critical radio signal. And they also need to provide time guarantees over Ethernet based networking. To solve these problems, the time sensitive networking, or TSN, ecosystem has evolved with different methods to make Ethernet a time critical communication layer. Let's take an example of a semiconductor manufacturing plant. The chips are produced through automated fabrication and photolithographic processes conducted on a piece of silicon wafer. And the silicon is an expensive part of that process. And the manufacturers always they want to pack more and more number of chips in a single wafer to save on cost. In order to do that, they use robotic hands to do very high density fabrication on the wafer. And then the wafer needs to be cut into chips with super accuracy. The accuracy of the movement of the cutting tool needs to be less than hundreds of micrometers, which means that the movement of the robotic hands are, they also need to be very precise. So these movements are monitored by the camera vision, vibration sensor, which keeps sending control signal to keep adjusting the position of the cutting equipment. And these messages have a very stringent latency requirement, as you can understand. I mean, these requirements are sometimes less than hundreds of nanoseconds for the whole process to work. Let's look at another example from the telecom domain. The 5G operators are interested in moving to flexible cloud RAN architectures, or also what is known as CRAN. And this CRAN enables the operators to address different application requirements by isolating the storage and the computing resources. They could be putting the storage and the computing resources at the base of the cell site, near to the antenna, or at a centralized hub hundreds of kilometers away, or maybe somewhere in between. For example, operators can support latency sensitive applications by using a multi-access edge computing data center that is located closer to the cell site. And as a result, a new Ethernet network segment is created that needs to carry that radio samples data, and which is very, very time critical, by the way. These 5G operators, they need a mechanism here to ensure that when the radio sample data are carried over Ethernet, they are delivered to and from the antenna within the time limit. In the broadcasting network, equipment such as audio video mixers, storage, and audio consoles, all these, they need to receive uncompressed audio and video streams without interruption of the control signals as they are, transported over the broadcasting infrastructure. And without a technology like AVB, which is a subset of TSN, all these devices were needed to be connected using audio video routers that have point-to-point connections to each and every endpoint for each and every feed. While an endpoint connected to an Ethernet interface can provide one-to-one, one-to-many, and many-to-many communication, that's the power of Ethernet-based shared networking. In some cases, the audio and the video is transmitted through separate channels. In a listening device like a TV monitor, the audio and the video needs to reach in synchronization so that the device can maintain lip sync while playing the audio and the video data. Just imagine how bad it will sound if my audio and my video are not synchronized when you are watching this. The industry needs a method for providing the Ethernet network with end-to-end bandwidth allocation, time synchronization, traffic shaping, and also predictable low latency. The IEEE AVB TSN task group has come up with multiple methods for solving these problems, which is known as the TSN standards. The standards work on the data link layer and comprises of tools which provides traffic shaping, bandwidth reservation, redundancy, frame preemption, and of course, time synchronization mechanism as an underpinning of all of these. The TSN ecosystem is really a toolbox of standards, and the tools need to be adopted as per the application need. The application needs of the industries, they vary a lot. And these application needs really drive the underlying network requirement, which are very different from each other. Here is a comparison in this table of the network characteristics of the industries that we are discussing today. For example, if you look at the table, the telecom fronthaul network for 5G are large compared to others here. And implementing something like redundancy is very, very complex, as well as expensive in this type of scenarios. Also, the telecom networks are not fully engineered networks, as you can imagine. And in non-engineered networks, it's very challenging to implement techniques like time-aware shaper. And therefore, these type of networks will need help from frame preemption, which is more appropriate technique in a non-engineered network. On the other hand, frame preemption may not be useful for the professional audio video network. They use high link speeds to carry high bandwidth data, and the benefit from frame preemption techniques diminish with higher link speeds. The automotive network, on the other hand, is static in nature compared to industrial or a professional audio video network during its lifetime inside the car. And therefore, dynamic configuration complexities are much less in designing TSN in an IVN. Also, the latency requirements for different industries are very different and driven by the application needs. As per this table from an IEEE document, it tells us that while something in the industrial may need sub-microsecond delivery guarantee, The automotive applications are mostly happy with tens of microseconds range. Infotainment is a bit more relaxed and it's in the milliseconds range. We in Keysight, specifically the IXIA solution group, are providing leading TSN test solutions globally. As a product manager of this solution, I have been providing TSN test solution to the leading vendors of all of these industries. And this is what we have seen from our experience about the adoption of TSN standards from different parts of the ecosystem. The table reflects the dynamics that we have just discussed in this presentation till now. Now let's move on to the second part of the presentation, where we will compare the validation strategies adopted by these industries. An industrial network is dynamic in nature, and new sensors, new machines can get added to the network during its operation. Also, the types of devices and the vendors are diversified. A new machine being added to the factory floor could be coming from a completely new vendor, which didn't exist earlier in the factory. Irrespective of this dynamic nature, the network administrator needs to have a method of maintaining TSN links, connecting these time critical components. Therefore, it's necessary for these new and existing devices to understand a common language and a centralized controlling model. On the other hand, IVN or an in-vehicular network is much more controlled and the changes are very less during its lifetime. So what we see in this slide is a centralized configuration architecture for a TSN network. The TSN enabled nodes in this network need to be configurable from the controller. Netconf Yang is a proposed communication channel in this type of cases, and as it is proposed by the IEEE 802.1 QCC and 802.1 QCW. The 802.1 QCW in fact defines the common configuration language or the Yang model for the time aware shaper or QBV. This is a must test for all the industrial switch vendors and the industrial system integrators as well. All our customers from that domain perform this test. One of the challenges that we faced as a test tool vendor is that the Yang model for time aware shaper was not fully standardized, and our customers were using their own Yang model for configuring their devices. And to be able to test these early stages of these implementations in their development stage, we designed a solution where we can run this test agnostic of the Yang model used by that particular vendor. So we have performed this test in the industrial forums like Industrial Internet Consortium or IIC Plugfests, and the results are made public in this test report that you can see in the slide. You can see the test report this is really public, and it provides many information on many other TSN tests performed in that Plugfest as well. And this is available in our website. The fronthaul network, on the other hand, is a result of a lower layer split that divides the radio stack between DU and the RU. And on the slide, these are the permissible latency values that are standardized by 802.1 CM standard for the fronthaul network. So between the RU and the DU, the one-way latency is 100 microsecond, which means if a fiber introduces 5 microseconds per kilometer, then this gives a budget of 20 kilometers. But we also need to consider the delay introduced by the switching elements in the fronthaul network. To solve this latency problem, 802.1 CM also recommends the use of strict QoS priority and TSN, and to be specific, the frame preemption mechanism. The fronthaul traffic or the EC-pre radio user data traffic is treated as express, and other traffic or any kind of management traffic present in that network is treated as preemptible. all the switching elements in that fronthaul network need to support the frame preemption capability. On the other hand, if you look at automotive networks, they're relatively lenient in terms of time sensitivity, and also traffic engineering is possible in those networks. Therefore, in most cases, frame preemption is considered optional or may not be required at all. But validating frame preemption requires sophisticated techniques. The network engineers from the switch vendors or the silicon manufacturers, they are using the IXIA tools to validate both the fragmentation capability and the reassembly capability of the devices. At a network level, the IXIA IX network can be used to measure the end-to-end latency of the express traffic and whether it is meeting the goal or the requirement as per the application. These tests are performed in presence of preemptible traffic, high network load, and malicious conditions. The crucial tests are to check how does the switch react when there are errors in the fragments, for example, or what is the impact of the preemptible traffic, what is the impact on the preemptible traffic latency when the express traffic is meeting its criteria. Now let's take a look at the time synchronization techniques and how they vary from industry to industry. The IVN is a domain-based architecture where there are components which can function in silos, disconnected from the outer world. In the network design, there can be network domains which are isolated from the outer world, and at the same time, there are network domains which needs to be connected to the outer world. As a result, an IVN can make use of multiple time domains. One that is using PTP timescale connected to the outer world, and the other one which is using internal timescale and which is isolated inside that IVN. But for an industrial or a telecom network, they are in most cases spread across multiple geographies and need to function with global components. And in these cases, time sync is provided by GPS and propagated by 1588. And in this type of network, the global PTP timescale is used. For a network like automotive with multiple time domains as defined by the new 802.1 AS 2020 standard, there are gateway bridges that needs to maintain multiple time domains. So validation is extremely critical for these type of architectures. As we can see in this slide, this is very common use case for an IVN gateway or a gateway manufacturer and OEM to ensure that the domain gateways are working fine and able to maintain both the PTP and the ARB timescale. Most of our customers are using IX network to perform this type of tests. Now, continuing this discussion on the time synchronization techniques, there is a difference in how the grandmaster rules are configured as well. In automotive, running a BMCA or a based master clock algorithm is not necessary, as the new node addition is not like a dynamic process in an IVN. In absence of BMCA, the standby grandmasters are the best option for maintaining synchronization in case of a failure. On the contrary, the grandmaster rules are not pre-configured in an industrial or a professional audio video network. Whenever there is a need for re-electing a grandmaster, BMCA is executed. So that brings me to the end of my session, and I hope I could provide some comparison of the different approaches used in adopting TSN in different industries. There are of course many other differences which I could not cover within this time frame today, but thank you very much for listening, and let me know if there are any questions and let me try to answer them.